Hey everyone, so after looking at the examples we had for the elevator lab, the apparent weight would tell you what the gravitational force would be read by a spring scale. So that means is if you're at rest, we know that you weigh exactly what the force of gravity is on you. Those forces are balanced and equal. Whatever the scale says is what you weigh. What we saw if there were accelerating scenarios, you could apparently weigh more or less depending on what your body's trying to do. So if the elevator was going to drop down and you were at rest, your body wants to stay at rest and the elevator drops out from underneath you. That's where you see the apparent weight drop. The force of gravity looks like it changes even though gravity is always pulling on you with whatever your rest weight is. In the case of weightlessness, that's when your apparent weight becomes zero. The scenario where this can happen would be if the cable was cut in the elevator and you started to fall. You and the scale would fall at the same rate, so you would never be able to push on the scale and the scale would never be able to push back up on you. So technically, you would be in free fall the whole time and your weight would read zero. In terms of astronauts, they have an apparent weight of zero due to this same fact, and we'll talk about that more in a section with circular motion and gravity. But technically, all astronauts are just in free fall, so they appear like they are in a weightless environment. Either scenario, if you are accelerating up, you can see the scales reading higher than the force of gravity down. But if you accelerate downwards, then that scale pushes up less on you because your body wants to keep doing what it was last doing. So go through that whole elevator scenario again if that doesn't make sense to you, and ask questions. I also asked you to do the Newton's third law challenge, where you had two people hook spring scales together, and one person would pull or the other one would not pull. I asked you what the reading on the scale was. The one big thing was that trial 3 there was not possible. If one person pulls to 8 newtons, the other person tries to pull to 14, whoever's pulling stronger, the scales will always read the stronger force. According to Newton's third law, Newton says that for every force, there must be an equal and opposite force. So if I push on you, you must push back on me in the equal and opposite direction. If you look at the case of the block on that table there, if you think of the force of gravity of Earth on the box, a lot of people think the equal and opposite force is the table pushing back up. It is equal, it is opposite, but it is not the Newton third law pair. If you look at the terminology there, it says force of gravity of Earth on box. If you look at the Earth, you see force of gravity of box on the Earth. That is an equal and opposite third law pair there. If Earth pulls down on the box actually pulls up on the Earth. And the reason the table actually pushes on the box is because the box runs into the table, and the table then pushes back up to support the box. Some terminology you have to get used to when we're dealing with a third law pair here. So we have 3 scenarios that I'd like to go through with you. I'll draw them out for you and show you where this third law pair comes from. So for scenario 1, walking out of the room. If I wanted to use my feet to walk out of this room, what I would have to do with my shoe is push backwards on the floor. If I push, that's you pushing on the floor. What the equal and opposite reaction is that the floor pushes you forward. So if I push on the floor then pushes me forward. If I want to walk backwards, I just reverse these arrows. I push forward on the floor, and the floor then pushes me back. In a swimming scenario, when someone pulls their arm out of the water and starts to swim, they push their hand into the water, they pull water back, so that's the force of you acting on water. What the equal and opposite reaction is the water then pushes you forward. So you push water back, water then pushes you forward. So when a rocket moves through the air or through space, it burns fuel. So it burns fuel and shoots fuel in one direction. The forces here are the rocket pushes the gas down and out. If the rocket pushes the gases down and out, or the gases, then push the rocket forward. So with a tire on the road, as the tire spins and it runs down and hits the floor, the tire pushes backwards on the road. That's tire acting on road, and the road then throws the tire forward. In all these scenarios, when you would draw a Freebody diagram of the object you're interested in, all you would care about are forces that are acting on the tire, not the tire acting on the road. You'd have to do a separate Freebody diagram for that. So if I just focus on the tire as my system, you can see that there's only one force acting on it. The road pushes the tire forward, and that's why you move forward. But the only reason you get that is because the tire pushed backwards on the road. And I know it sounds like I might be saying the same thing over and over again, so if that is not clear, please ask me questions tomorrow. Which brings us to the famous example of the cart and the horse. To make the cart go forward, the horse must pull on the cart. But if the horse pulls on the cart, doesn't the cart have to pull back on the horse? And then if that's the case, how does anything ever go anywhere? If you look at this scenario here, the horse is pulling the cart forward, the earth is pulling down on the cart, the ground is pushing up with the support or normal force, and the ground is causing friction back on the cart. So if I look at this free body diagram here, it looks like there might be an unbalance of forces forward here, which means that the cart can accelerate to the right. Well, then let's look at the horse. Yes, there is a backwards equal and opposite force of the cart pulling back on the horse right here. So there's that third law of pair, but it is a force that is acting on the horse. What's going to happen to make the horse actually go forward is that the horse is pushing on the ground backwards, and the result of that force is the ground pushing the horse forward. As long as that force from the ground is bigger than the cart pulling back on the horse horse can move forward and accelerate. So we want to try examples here of drawing free body diagrams with things in any scenario you could come across, like this box on an inclined plane. When you come across an inclined plane, it's not that big of a deal. You want to tilt your XY axis so that you have some parallel forces here. What I suggest is tilting the XY plane like this, making that X and this Y, and you'll see in a second why I'd want to do this. Okay, so I want to draw a free body diagram for this box on an inclined plane. As you go through your list of forces, gravity, normal force, friction, applied force, tension, springs, you got to think about what is acting on the box. First one everyone loves to go to is gravity. Gravity is acting downwards in this scenario. And we have a perpendicular support force, which we call our normal force. So these are the two forces acting on this box. If I want to determine how the object is actually going to move here, the object is going to accelerate. What I need to do is determine the net force, and if my net force is balanced or unbalanced. Looking at this scenario, I can see a force up and to the right and a force straight down. I can already see and visually tell that there must be some net force down the hill. How can I tell that? Just take your vectors and do some vector addition. The normal force plus the gravitational force leaves you a net force down the hill. Just by vector addition, I know that I have a net force, and that net force points downwards. Let's show what I mean by tilting the XY plane and how that's helpful. So if I wanted to keep myself organized with X and Y forces here, I can make myself a little chart and say, well, I know that there's a normal force acting on the box, and I know that there's a gravitational force. Those are the two forces we saw in our scenario. Those two must add up to the net force. But since forces can be in more than one direction, you need to make sure that you have all of your forces accounted for in all directions here. If I draw back on the normal force and the gravitational force, it's tough to see which one is in the X and which one is the Y. If I just make my axis straight up and down with X and Y, what you can see is that gravity is straight up and down in the y, but the normal force is tilted in the x and y direction. And to make things simple for us, it's a lot easier to tilt the x-axis and deal with a normal force that's in one of the planes than deal with a tilted normal force. Tilt your axis. Make x go down the hill and y go perpendicular to the hill. So if I start to figure out which force is in which direction, I go, well, the normal force are not horizontal on my tilted plane, so there's no force here, but the normal force is in the vertical direction. And I'm going to put a plus in there because forces are vectors. So it's a positive normal force in the y direction. Now gravity. Gravity is tilted. Gravity is along this part of my xy plane. So it is an angled force, but we can use some geometry here. This angle theta down here, call it 30 degrees. That would make this angle up here 60 degrees, if this is 30. So that means this inside angle right here on my tilted plane must also be 30 degrees. So really what I've done is I've taken this force here and broken it into two pieces. This is my gravity in the y direction, and this is my gravity in the x direction. Going back to my xy plane there, what I can say is that, okay, there is a force of gravity in the y direction. It's negative mg, and look at your trig. There's the angle of the hill. Mg looks like it's cosine since it's adjacent. And since the object is not accelerating in the y direction, we can make sure that this ma cancels to 0. So what that tells me is that the normal force, what the ground has to actually push, is only mg cosine theta. In the x direction, the only thing left here is this guy. That's the only force in the x direction, so I can write that as mg sine of theta. If I look at my x direction, I've got 0 plus mg sine. That's going to equal ma. I want to figure out the acceleration of my system. I can say that mg sine of theta equals ma, and the nice thing is there's a mass on both sides. I can divide that mass through and find out that the acceleration of this box going down the hill is just g sine theta. So when you have a tilted hill, the reason it accelerates is because there is a force of gravity pointing down the hill, and that force of gravity is equal to this mg sine theta, which causes masses to accelerate, so your acceleration is just g sine of theta. You can also have forces that are at angles. In this scenario, I see 3 forces. This dog is now pulling the sled up at an angle instead of straight to the right. In your free body diagram, I see gravity down, the normal force up, and an applied force at an angle. What I can do with that applied force is look at its 2 pieces. So there's the force applied in the x direction, and here's the force applied in the y direction. So if I break this into its x and y pieces to organize my forces, I can say I've got an applied force, I've got the force of gravity, and I've got the normal force. Remember, all of these forces must add up to my net force, and we know that net force must equal ma. So if I look at my applied force, I do see a force in the x direction. It looks like force cosine of theta. There is a force in the y direction, so it looks like force sine of theta. The gravity is pulling straight down, so I'm going to put minus mg, since that's how we calculate the force of gravity. And it looks like the normal force is straight up. Gravity is not in the x direction, and normal force is not in the x direction. So if I wanted to say, hey, what's making this thing accelerate? The only thing it's making this accelerate in the x direction is f cosine theta. So f cosine theta would equal ma, and you could figure out the acceleration of the block. However, if you look at the y direction, The y direction has 3 forces in it. And we know that this y direction must sum up to 0 because the sled hasn't flown off the ground or fallen through the ground. What you could say is that the F sine of theta, the applied force upwards, plus normal force minus gravity must add up to 0. So if that's the case, you can say that the weight of the object is equal to the applied force component that's up and the normal force. So this is where you want to be careful and never assume that the force of gravity will always equal the normal force. A lot of people want to say that these two forces here are always equal and opposite. You've got 2 up forces and 1 down force. So since they are balanced, the 2 ups must equal the 1 down. So what you're actually doing is you're taking some of the normal force off the ground, which is kind of nice and will be really helpful in the next chapter.